We only done 2 questions. They took forever in the day, really, speeding up and slowing down. We're going to move on to doing these questions and then finishing off. So what kind of things are you going to be asked to do when you're dealing with applications? Well, you're going to be asked about a moving object, and you're going to find out, or be asked to find, when it reaches its maximum height. Now, when an object is traveling, I kind of like the up and down one. When you imagine an object, and this is time, and let's say this is height, then it, like throwing a rock, it goes up, and then it comes back down. The maximum height they're looking at happens here. And we know that at that point in the curve, the tangent line is 0, which means the derivative is 0, which in turn means the velocity is 0. So when you're being asked to find when does an object reach its maximum height, you're trying to solve the equation, when is the velocity 0? You know, that'll involve factoring or quadratic formula or whatever it might do. Now, when you want to know when an object hits the ground, you're trying to find out the position is 0. So trying to solve when is the position function 0. I mean, there, you hit the ground there. When you want to know when is an object on the way up, so for instance, in this case here, from there to there is on the way up. Let's pretend that's 3 seconds. What you're trying to do is find when the velocity is greater than 0, and when is it on the way down, you find the velocity is less than 0. So these are the kinds of questions that we're going to be doing in 3, 4, and 5. Let's start with question 3. So in this case, you're told the height of an object, and it's given by a rather ugly combination of numbers. Which is kind of what happens if you do real engineering. It's given by that. And the first question is asking us to find what the velocity at the 2-second mark is and what the velocity at the 4-second mark is. Well, you want the velocity, you just differentiate this guy. So the velocity at any given value of t, I'll differentiate the number, you get nothing. Differentiate that, you get 23.5. And this one, you multiply by the power and you reduce it by 1. So you get negative 9.8 t. So you want to know the velocity at the 2-second mark, plug in 2 here. You want it at the 4-second mark, plug in 4 here. I'll just do one of them. Let's do 4. So that would be 23.5 take away 9.8 times 4 seconds. 23.5 take away 9.8 times 4, and I get, well, if I hit it right, I will. 23.5 take away 9.8 times 4. I get an answer that is negative, which just means that I'm kind of like here, right? I'm heading downwards. Are we okay with that? So if you want to know the velocity of an object that's been thrown up in the air, you find the velocity, and then you evaluate that velocity at whatever number that it's asking. So in question B, it's asked us when does it reach its maximum height? We know it reaches its maximum height when the velocity is 0. So we are going to solve that guy. And even although the numbers are not pretty, the math is pretty much the same, even if they were nice. So what you would do to solve this equation Well, as long as you do it to both sides, it's okay rule. So how about subtracting 23.5 from both sides and then dividing both sides by negative 9.8. So since there are two negatives, that means the answer is positive, so I won't even put them into the calculator. 23.5 divided by 9.8, and they want the answer to 2 decimal places, and so that's 2.397. 3 becomes 4, so it's 2.4 seconds. And then it asks, what is the maximum height? So they're basically asking you for that number over here. So all you need to do is find the height at 2.4. So that's 4 plus 23.5t, take away 4.9 t squared, and you find it at 2.4. Bit crushed here. Hopefully you can adjust it. So it's going to be a 4 add 23.5 times 2.4, subtract 4.9 times 2.4 squared, and to 2 decimal places, that's 32.18. I think the units were meters. How are we doing so far, guys? Right, so if you tell me a formula that gives me the height at any given time t, if you want velocity, find the derivative and evaluate it at any point you like. If you only want to know when it reaches the maximum height, solve when is the velocity 0, and then you can plug it in to find out what that maximum height is. Now the next question is asking, when does it hit the ground? So a when means t equals you're trying to find. So when does it hit the ground? So we are trying to solve when is the height 0. We are trying to solve that ugly equation. Any ideas? How do you solve such an ugly looking quadratic equation? There are two ways. One is easy, one is hard. And you don't need to tell me the answer. Be amazed if you could. It's too messy. But how would I get the answer? Formula? Yeah, I could. Anybody who's used the quadratic formula, is it a very convenient formula or is it kind of ugly?
I don't think it's that bad.
Oh, well, that's good. A lot of people find it kind of ugly, especially when you use numbers like these, right? So let me show you an alternate. You don't need to do it this way, but there is, I hope you're looking at Desmos, there is the function that we were dealing with. And this is what it looks like. Now, if I click on that guy, can you see it hits the ground at 4.96? Yeah, that's it. Would you agree that's kind of nice, graphical? Any questions about that? Okay, then we move on. The next thing they ask you, in fact, I think it's the last thing also. What's the velocity when it hits the ground? Well, I know the velocity function. We've got that from here. And I know where I should be looking, which in this case is 4.96. So it's just a plug and chug. And if you do all of that, you end up with the answer negative 25.11, and the units are meters per second. The fact that this velocity is a negative number, what is that telling us in kind of the situation? What's going on if a velocity is negative?
It's going downwards.
Does that make sense? If you imagine, it goes up and it goes down, right? Boom, right? Would you agree when it hits the ground, it's coming down the way? So that makes perfect sense, doesn't it? It would have a negative velocity. Useless piece of information, but it's in my head, so I'll tell you it once. I remember watching a program where they were talking about ballistics, right? Things that get shot, essentially. And the question was, do you know how in some countries when they're all celebrating, they all get their machine guns and they shoot them in the air like in movies and whatever, right? And you think, well, I used to think, what happened to all those bullets? I mean, they didn't go into space, right? Because they're not that fast. And the answer is kind of boring. They come back down again. And unless you fire them, unless you fire them vertically upwards, they'll come back and hit you in the head. But normally there's a slight tilt and the bullets land somewhere else. So they could last, 500 meters away. So actually, you shouldn't be anywhere near idiots that shoot guns in the air. You are nodding as your sergeant told you, don't ever, ever do that. Santiago. Right. Would you get into trouble if you just randomly shot your gun in the air?
Yeah.
Right. So I just wondered, and then the guy told us, and I thought, oh, it's kind of obvious the bullets come down. And they tend to come down with almost the same velocity they went up the way, so they're very dangerous when they come down, right? You could get killed. Useless piece of information, but that's essentially what's happening, right? Bullet going up, bullet coming down. Of course, there's a thing called terminal velocity, which means that they only can, there's a maximum speed that they can come down at, but that's still enough to kill you. Oh, shush. Our dogs are doing the people on the roof are coming thing. I apologize for the next week. That's going to be probably our lives. Hopefully they will settle down. Okay, so the only version of that list of questions that I talked about there, and the only one that we haven't covered is when it's on the way up, right? And when it's on the way down, okay? And it's on the way up when the velocity is positive, and it's on the way down when the velocity is negative. So let's show you a version of those questions. Number 4 as an example of that. Here, the function is 160t, take away 16t squared, that's much nicer to deal with. I won't do A, it's another maximum height question. So if you wanted to know what the maximum height is, wouldn't you differentiate it to get the velocity, make it equal to 0 and solve? And then plug that value of t in to here to find out what height that would be. So that would be another one of those guys. Now the question they do have is, what is the velocity of the ball at 384 feet above the ground and on its way up? And what's the velocity of the ball when it is 348 feet on the way down? Oh, so that's not quite what I thought, but that's fine. you want to get the velocity, differentiate. Now, the time that they ask us is hidden because it told us that the position, the position was 384 feet. So you can imagine a little dotted line here, and this is at 384 feet. On the way up, it's going to be that value of time, and then on the way down, right? So on the way up, on the way down. So we need to solve, when is the height 384 feet? And that means solving an ugly quadratic. And if you add 16t squared, take away 160t from both sides, you end up with that. Now you could, I'm sure it's possible, but I wouldn't want to do it. Couldn't you factor that? Or couldn't you do the Desmos thing I showed you? And just find out when it is 0 and call it good. Let's try factoring it. I feel brave. Plus the numbers are nice, so I think it's doable. I try not to factor quadratics with big numbers. So is there any common factor you think might work with those three guys?
Would 16 work?
I think 16 works. I'm about to find out. That's easy to do. That's easy to do. Fingers crossed that that guy works with 16, right? Now, 384 divided by 16. Please be a nice number. And it is. Would you agree that's a much easier quadratic than that guy is? So I'm looking for volunteers here. Two numbers that multiply together give you 24, but when you combine them, you get -10. So that must mean that they're both negative then.
Negative 64.
Right. And won't t equal 4 be on the way up? And won't the other solution, t equals 6, won't that be, whoops, let's not get there, won't that be on the way down? So all I need to do now is find the velocity when it's 4 and the velocity when it's 6 and call it good. So that's all I want to do for that question. I think there's one more, is it 5? In 5? Nope, that's it. We're done with that section. So we've done that, guys, we've done that guy, and we've done that guy. So there is only one more thing for us to deal with, and that is essentially general rates of change. All yesterday up to this point in time today, we've been dealing with moving objects, right? The position of the function is 2t squared plus 5t cubed, right? That stuff. Now we're going to look at just everything else, right? And rate of change is essentially derivatives. So if you ever find a question that says, what's the rate of change of this? Or what is the rate of change of that? You will say, oh, you want me to differentiate the formula with respect to whatever the variable happens to be. So let's just give you some practice at what finding a rate of change might look like. The area of a circle is pi r squared, agreed? If I wanted to find the rate of change for the area of a circle, I would be finding its derivative. Now, in this case, won't r be the variable, right? So this is like pi x squared. So multiply by the power, reduce it by 1. The volume of a sphere is 4/3 pi r cubed. If you didn't know that, I've just told you. Its volume is 4/3 pi r cubed. If I want to find the rate of change at which volume is changing, it's a power rule. Multiply by the power, reduce the power by 1. Are you comfortable that if I give you a formula, you can differentiate a formula, even if you've never seen it in your life before? For instance, you may not have ever seen this formula here. I'm trying to find one. Q of t, which is the amount of charge that is in a circuit at any given time t, so it would probably be a capacitor, is given by that. If they went and asked you to find the rate of change, you would differentiate. So the key here is, if you want to get the rate of change of something, just differentiate that something. Does that make sense? Even if you've never seen a formula in your life before, don't you know, if I tell you the formula, don't you know how to find its derivative? Now, certain questions have names for the rate of change. For instance, do you know the rate of change of this one here? It's called current. So if you're into electricity, you know what I'm talking about. Right? But it's still a rate of change. So the basic kinds of questions you're going to get is, here is a formula and differentiate it. And sometimes, almost like magic, you see things that you didn't expect to see. Right, let's do this one. Pi r squared is the area of a circle. Its derivative, right, its rate of change is 2 pi r. Do you recognize the formula 2 pi r? You've seen 2 times pi times r.
Yeah, it's the length around the circle.
Yeah, it's called the circumference. So the rate at which a circle increases in size is equal to its circumference. If you imagine a circle growing, right? Doesn't it kind of grow like a tree ring, right? By circumferences. Right? Each extra layer is like a circumference worth of area. This one you're less likely to know, but this is the volume of a sphere. If you differentiate it, you get this guy. Just an off chance, does anybody know what 4 pi r squared is in connection to a sphere? That's the surface area of a sphere. In other words, if you painted the outside of a sphere, how many square feet would I need to do it? That's the guy. I think it's kind of interesting that you get things like that. So the kinds of questions that we're going to be dealing with are basically 6 till we get to the end. So let's jump right in and pick one and kind of get you used to the way they phrase it. What's that one? Is that to here? Question 7 says a stone is dropped into a lake, creating a circular ripple that kind of goes outwards, of course. And it goes outwards at speed of 60 centimeters per second. Find the rate at which the area of the circle is increasing after each of the following. So in question 1, you're being asked to find the rate at t equals 1 second, and then 5 seconds, and then lastly, 6 seconds. So I know the area. I know the derivative, so that's going to get me the rate of change. And I want to know it at, say, the 1 second mark. then it's just 2 pi times 1. And you don't actually turn it into a decimal. We want exact values, so you just call it 2 pi, and the units are square centimeters because it's an area per second. If you wanted to note at the 5-second mark, it's 2 pi 5. Off you go and calculate your other things. Now, different version. The volume one. Try to read these questions. It's not as obvious as it seems to me. Let's do my own. That's probably a good way to start. Let's suppose I have a circle that looks like that. And suppose I tell you that radius is increasing at the rate of 30 meters per second. That's just them telling me the R is 30t. So when they tell me the rate, they're actually telling me that. Now, if I go to my formula, then the radius is now this guy. So now I have a slightly different formula for in this world, the circle doesn't have a fixed radius, it has a radius that's changing through time, which is a little bit more realistic. Now, if you want to find its derivative, multiply by the power, reduce the power by 1. And you want to find the rate at time equals 1 second. What's the units? Meters per second, so it's going to be square meters per second. And if you wanted to find it at the 5, that's much better. Yeah, this one is much closer to question 6. And what will that be? Oh, God in Himmel. 9,000. There we go. Okay, let's choose. Let's try and model a sphere exploding. So can you imagine you've got a little sphere and it blows up into a big sphere, right? Like a supernova. Well, I know the volume is 4/3 pi r cubed. Suppose I tell you that the radius, right? So the radius of the sphere is growing with time, and it's growing at the rate. So they're telling me the rate at which it's growing is, say, 100 meters per second. So that it's growing really fast. Then my formula for the volume gets changed a little bit. Because if you tell me the rate, then R is 100 times that. If this was 50, this would be 50 times T. Wish I'd thought this one through before I made it up, because it's 1,000,000 pi T cubed. And you want to find the rate, you find the derivative. And that's going to be multiplied by the power. So that's what essentially 4,000,000 pi t squared. So you multiply this by 3 and then reduce the power by 1. They cancel. 4 times that gets you 4,000,000 pi t squared. So if you want the rate of change at the 1 second mark or at the 10-second mark, just plug in 1 there, just plug in 2 there. That's a big growing explosion, isn't it? Imagine a little thing going. I think I've just modeled a version of the Big Bang. Tiny little thing exploding into a big thing. I'm sure the numbers for the Big Bang are a lot different. Let's try question 10. Here you have a formula. I think it's called, after an Italian guys, Torricelli. There it is. So I'll give you a little story what's going on here. Imagine you've got a tank. And this tank, when it's full, has 4,500, what's the units? Liters of water in it. Oh, gallons, yes, okay. And there's a hole, and out spurts water. And the amount of water left, right, after t seconds is given by this formula. So you can imagine after 1 second, there's a little bit less, after 10, after 20, and the water is shooting out, right? Now, this formula models water or anything coming out a tank. And it's actually quite realistic. Can you imagine that you had a full tank and you've a burst? What's the rate at which the water comes out? Well, it changes. Right at the beginning, doesn't it shoot like a bullet? Because there's a lot of water and it's coming through that hole and off it goes. But once the tank kind of gets to about halfway, isn't that the rate at which the water is shooting out, isn't it decreasing? And then when it's almost empty, isn't it almost like trickling out at the end? So this formula that tells you the volume that's in the tank at any given times t, if you differentiate it with respect to t, what you're finding is the rate at which the water is leaving the tank. Well, although it is kind of messy, it is doable. Isn't this a chain rule with some ugly values, right? This bit here is your inside function. So I'm about to differentiate it. Multiply by the power, that gets me 9,000. 1 minus 1/50th t to the power of 1, right? So multiply by the power, reduce it by 1. And then don't you finish with the derivative of the inside function? What is the derivative of this guy here? What's the derivative?
150th.
Yeah, negative 1/50th. And that makes my answer to the rate of change of the volume as negative. That and that can simplify, so I'll just figure out what that is. 9,000 divided by 50 comes out to be 180. 1 take away 1/50th t. So that tells me the rate at which the water is shooting out that hole. So let's evaluate it at certain places. Suppose we are interested in the 1 second mark. So the rate of change at the 1 second mark is negative 180, 1 take away 1/50th times 1. I'll tell you what that is. And the answer is negative 176.4 gallons a second. And then I'll wait a little bit later and I'll do it maybe, so that's at t equals 1. Let's do it at t equals 20. I'll do that calculation now. Negative 180 1 minus 150 times 20. And that's going to be 180 times negative 108 gallons a second. And then I'll do it at the 50-second mark. And I don't actually need my calculator for this one. We'll see in a minute why. At the 50-second mark, won't that be 1 and 1 take away 1 is 0? And so the answer is 0 gallons per second. So, full tank, hole gets punched in it, out shoots the water. At the 1 second mark, isn't it shooting out at 176 gallons a second? You do not want to be near this. Isn't this shooting out like a bullet? 176 gallons a second is a lot. It's negative, isn't it? Because isn't the volume decreasing, right? That's why it's a negative number. Now, if you wait to the 20-second mark, would you agree that it's got substantially less powerful? And at the 50-second mark, the answer is 0. What is special about 50 seconds? What's happened to the water in the tank at the 50-second mark? Why is there no more water coming out the hole?
There's no more water in the tank.
That's it, it's empty. Would you agree eventually everything empties, right? It's not infinite. So this formula is very useful for predicting how water or anything. Can you imagine that you had a big oil tanker and there was a hole in it? Wouldn't a version of this predict how much oil would be shooting out of that through time? Right at the beginning, when the tanker is full, isn't there a lot of oil popping out it? Right, and then it kind of drifts away and drifts until basically it's empty. Now, you don't need to know anything about physics. I just added the story. If I gave you this formula, right, and I asked you to find the rate of change, wouldn't you just differentiate it? And then if I said what's happening at 1, 20, or 50, wouldn't you just plug 1, 50, and 20 into that and you get your answer? Right? You don't need to know physics to be able to answer these questions. So the next one I'm going to do is about electricity. And you don't need to know anything about electricity to do this. The formula for the amount of charge is given in this particular circuit by that. And they ask you to find the current when T equals 1 second. Okay. You don't know physics. Gotcha. Don't know electricity. But you do know calculus. And you should know, although I think they tell you, that when you want to find the current, that word there is just the rate of change. So you find the derivative. Power rho, multiply by the power, reduce it by 1. Now you want to find the rate of change, the current at the 1 second mark. The answer is 1. And evidently the units of current are amps. So you just stick an A at the side, but WebAssign does the units for you, so don't you worry. So here's a puzzle. When is the current? I'm calling that the rate of change. lowest. Okay. Here is the guy you're going to deal with. And they're saying, when is the current at its lowest? Well, that guy tells you the current. That guy tells you the charge. So if they said, when is the charge the lowest, wouldn't you be looking for when is this guy the smallest number? And that would be when is its derivative of 0. But we want to know when this guy is at its lowest, right? Now, if you put that into a calculator, wouldn't it look something like that? So you're looking for here. So you've got to be careful with this one. I'm going to take this guy here, and I want to find out when it hits the bottom. Now I can do that a couple of ways. Couldn't I just plug that into Desmos and find out where the bottom was? Couldn't I use the formula that you picked up in Math 141 that tells you the x coordinate of the vertex? Wouldn't that work? Or I could do this. Couldn't I find out when that guy is 0? Well, if you differentiate this guy, you get 6t take away 8. And if you solve for t, the answer is 4/3 of a second.
So you differentiate the current again?
Yes, so here is the only other time we've ever done that was when we wanted to find acceleration. Remember, acceleration is the derivative of the velocity. So in this case, we differentiated again. Or you could have done it the other ways, right? You could have just said, okay, I know what that looks like. I'm trying to find when that happens. All three ways that I mentioned actually would end up getting you the same answer. So it's not like they are different from each other.
So the first derivative of charge is the current, and the second derivative, is it still called the current?
No, I have no idea what they call it. I don't really, it doesn't matter what they call it, right? I can still do it. I mean, if I was into electronics, I might have a name for it. Probably they do. I just don't know what it is. But it doesn't stop me from finding the second derivative, right? And solving. That was a little bit of a head scratcher. A couple more. Oh, which one have I time for? Neither of these are going to be quick, but I'll do my best. Here is a formula that models D. And what's D? Oh, the depth of water in a harbour. So the depth at time t is 7 plus 5 times the cosine of a really ugly and therefore probably realistic equation. 7 plus 5 cosine of this ugly guy. I'm going to rewrite this guy a little bit differently. It's also going to be even uglier. And that times that is the ugly part. 0.503 times 6.75. So take away 3.39525. So I can imagine that, at different times of the day, can you imagine the water level going up and down with the tide? And if you put in 5 here, this would be the depth of water in the harbour, right? Maybe like that one. And you put in 6 and then 7 and then 8 and then 9 and 10, 11. You want to go up and go down, from low to high tide. And this formula here tells us how to do that. And we are being asked to find how fast. Now that is the same thing as asking for the rate of change. So if you ever see a formula and you don't know what to do with it, do you know a good bet is that you're going to differentiate it. So they want me to find out how fast the tide is rising or falling at 2 AM. So that's at t equals 2. So I'm going to find the derivative. And that is ugly, but it's still doable. Derivative of 7 gets you nothing. Okay, what do you get if you differentiate 5 cosines? What's the derivative of 5 cosines?
-5 sine.
Of this horrible expression. Okay. And then shouldn't you finish with the derivative of the inside function? Now, as ugly as that looks, isn't its derivative just 0.503? So you finish with a 0.503. And I'm going to multiply them together just to make it a little bit more together. So 0.503 times 5 gets me negative 2.515, the sine of this guy. So when you plug in 2, so it's negative 2.515, the sine of all this stuff, times 2, take away that guy. You'll hit a whole load of buttons. And I have the answer in front of me, so I'm just writing it down. You get that. And the units are meters per hour. And they tell you that in what the units are. This is rounded off to 2 decimal places. Hey, come on, guys. If you plugged in t equals 8, the rate at which the water is changing, the tide is changing, is negative 1.48 meters per hour. Okay. At the 2-second mark, the answer is 1.72, and at the 2-hour mark, I should say, 1.72. At 8 AM, it's negative 1.48. At 2 AM, isn't the water rising? So, right. And at 8 AM, isn't the water going down? So won't there be some place between 2 and 8 where it stops going up and just before it's about to start going down again, right? And at that point, wouldn't there be high tide? Right, that'd be the highest point in the harbor. How could I find when that was? What will this derivative be equal to when you reach high tide? There.
0.
Yeah. Now, nobody in the right mind would want to solve this equation, right? Let's do the better one, right? This equation here. Would you agree you wouldn't want to solve that algebraically? So couldn't you just plug it into Desmos and find out when it's equal to 0, which is basically when does it cut the x-axis? And of course, it goes up and down forever. So you'll be able to find, you know, each day at what time the high tide was. Well, if